Hello everyone and welcome to week 2. So to start with this week, let us work on a simple neural network so that we understand mathematically what exactly we mean when we say forward propagation and backward propagation. For this lecture, we will be going to use a neural network as shown in this slide, which has two inputs, I1 and I2, which has a hidden layer with two neurons H1 and H2 and an output layer with again two neurons O1 and O2. And of course, you have the weights assigned for each of these neurons. So for the neuron H1, you have the weight W1 and the weight W2 coming to it, whereas for the neuron H2, you have the weight W3 and the weight W4 coming to it. Similarly, for your output layer and its first neuron O1, you have the weight W5 and the weight W6 coming to it. And for the neuron O2 of the output layer, you have the weight W8, which is actually coming from H2 neuron, and the weight W7, which is coming from the H1 neuron. And of course, as we know, for a neural network, apart from the weight, we also have the bias. So I have my bias B1, which goes to the neurons in my hidden layer. So here and here. And then I have the I have the bias B2, which goes to the output neurons O2 and O1. And to start with, these bias is given a value 1. So this is our neural network that we will be working with. So the first step, so in order to get started, we have to assign some numbers to the weight and the bias. So let us give some numbers to initialize the weight and bias and the training input and output. So let us say that I1 is 0.05. So my input I1 is 0.05. The input I2 is 0.10. And then the output which I expect, my target output from O1 is 0.01 and my target output from O2 must be say 0.99. So now I have my input. So when you have a training data set, this input are the ones that is present in your training data set in the form of columns or attributes, and your target Y values will be also present as columns. So this output will be also present in your data set if you are working with a labeled data set. Now let us come to weight and bias. So this is exactly the process what happens during the weight initialization. So in my week 1, I have talked about weight initialization and different methods of weight initialization like random initialization, zero initialization, or Xavier or he initialization, and so on. So what happens is that in order to actually start working or start my forward propagation, I need some weight values to be assigned to my W1, W2 up to W8 along with my bias B1 and B2. Now let us go with a random initialization and say that the W1 is assigned with 0.15, W2 weight is assigned with 0.20, W3 is assigned with 0.25, and W4 weight is initialized with say 0.30. And similarly, the random initialization for my W5, say it is 0.40, W6 is 0.45, W7 say 0.50, and W8 say 0.55. Similarly, I also need to provide some weight initialization for my bias. So say that B1 is 0.35 and B2 is 0.60. So this is exactly what a weight initialization means. Depending upon the algorithm that you have chosen for weight initialization, an initial weight will be added to your network so that we can start our forward propagation. Now in this example, I have used a random weight initialization. So because of that, the random values will be initialized to my weights and my bias. So the goal of backward propagation is to optimize the weights. So we have initialized our weights. So the goal of our backward propagation will be to optimize these weights so that the neural network can learn how to correctly map your inputs to the output. So for the rest of the video, we will be going to work with a single training set with input 0.05 and 0.1, and we want the neural network to output 0.01 and 0.99. So let us start with the forward propagation. In forward propagation, the goal of your neural network is to find the total loss, or what we call as the total cost or error of your neural network. That is, based on the weight we have initialized for our neural network, how close is my predicted value of y with the actual value of y. So based on our labeled data set, the actual value of y or the target value of y is 0.01 for your output layer O1 and 0.99 for your output layer O2. So during the forward propagation, what we are trying to do is, we are trying to find out what is the predicted value of y based on these weights that we have initialized, and how close it comes to my actual value of y. So let's get started with it. So let us first find out how to calculate the total net input for each of the neurons beginning with our first neuron, which we will select as H1. So beginning with the neuron H1, which is the first neuron in the hidden layer, let us calculate the total net input. So the total net input for the layer H1 or for the neuron H1 is equal to, so for this neuron H1, what are the weights that is associated with it, or what are the weights which is coming to it? It is nothing but the weight W1 and the weight W2. So those are the two weights which influence my first neuron, which is H1. So its net weight would be NH1 is equal to W1 into I1. So W1 into this I1 plus, as you might have guessed by now, W2 which is coming from I2. So W2 into I2 plus the bias that is coming to it, which is B1 into 1. So when I substitute these values, W1 is 0.15 into I1 is 0.05 plus W2 is 0.20 into I2 is 0.10 plus B1 is 0.35 into 1. So when you do this calculation, you get the net H1 is equal to 0.3775. So remember from the first week's video when we discussed about a neuron, you might remember I have shown you a figure wherein which I have divided my neuron into two parts. The first one which does the summation, right? It does the summation of weight into your input, and the second one was the activation function. So the activation function, right? So I have completed the first part, which is the summation. Now let us see this value, what happens when it goes through the activation function. So we now squash this value of net H1 by passing this value through a activation function. And for the purpose of this lecture, I have chosen sigmoid activation function. So sigmoid activation function, so it is nothing but I write out of H1 is equal to sigmoid activation function is 1 by 1 plus e raised to minus x, which is equal to 1 by 1 plus e raised to minus net H1 in our case. So that is equal to 1 by 1 plus e raised to minus 0.3775. Now, if you are someone who is not sure of the calculation of e raised to minus 3775, now there are calculators available online for this. So you could just give this value and you could find it out for yourself. So since I have already found it out, my out H1
will be 0.593269992. So here E is called as the Euler's number. So Euler's number, and its value of E is approximately 2.718. Now again, as I have mentioned, there are online calculators available for this, so you don't have to worry on how I will be calculating this. You can find it online. So once you do that, your out H1 is this value. So we have found our net input for our neuron H1, and we have to continue this process for all the neurons in my neural network, of course, except your input layers. So you have to do it for H1, the same process for H1. You have to do the same process for O1 and O2. So technically, you will have to also find net H2 by the same process we have done. You have to find out then, of course, out H2 by passing that value through the activation function, right? Now similarly, you will have to find out net O1 for your first neuron of your output layer. Now that has to be passed through the activation function to give you out O1. And last but not the least, you do have to do the same process in order to find net O2 and then pass it through the sigmoid activation function to give you out O2. So these steps has to be completed. So please try that at home and find out what are the values you will be getting for these parameters which I have mentioned.
So we have calculated the net input for my neuron H1. So that is net H1 is equal to 0.3775. And we have then passed it through a sigmoid activation function, which is 1 by 1 plus e raised to minus 3775. Now this is the website wherein which we can find out e raised to any expression. So for example, from our problem, we need to find e raised to minus 3775. So e raised to minus 3775 is 0.68557. Now after that, we have to find 1 divided by 1 plus e raised to minus x. So here we have 1 divided by 1 plus e raised to minus x. From this is 0.6855, and once I do that, I get the value to be 0.5932. So that is how I get this value 0.5932. Now, after that, let us go ahead and do the same procedure for H2. So here I have computed net H2 and then I have passed that value to my activation function in order to find out H2. So as you can see, net H2. So net H2 is nothing but which all weight influences my H2. So that is W3 and W4. So W3 into I1. So it's coming from the I1 input and W4 from I2. So W4 into I2 and then of course the bias. So that is the equation here. Once we calculate this, we get the value as this. So once we have done the summation, it is now time to pass it through our activation function. So once we do that, this is the value which we get for H2. As I have mentioned before, we now need to do the same procedure to my node O1 and node O2. So let us start with node O1. So for node O1, the weight that influences is W5 and W6. And where do this weight come from? For example, W5 comes from H1. So H1 nothing but out H1 which we have previously computed, right? So and W6 is coming from out H2, right? So for my net O1, I have W5 into out H1 plus W6 into out H2 plus of course the bias that is coming from here, which is B2. So that is B2 into 1. So when I substitute those values, my net O1 is this. Now after that, again the same procedure, pass it through my activation function and we get the value of out O1. And finally, we do the same procedure for my node O2. So I need to find net O2. So net O2 is influenced by the weight W7 which is coming from H1. So W7 into out of H1 plus W8 which is coming from H2. So plus W8 into out of H2 and plus of course the bias B2. So this would be our equation, and substituting the value for W7 which is 0.50 and then out H1. So out H1 is something which we have already calculated while we were doing this hidden node. So we substitute that value plus W8 is nothing but 0.55 into out H2 plus 1 into B2 which is 0.6. So you get the net O2 value, pass it through the sigmoid activation function in order to get your out O2.
So we have now completed the step 1 of my forward propagation, which is to calculate the predicted value of y, right? And the predicted value of y is nothing but the out O1 for my first output node and out O2 for my second output node. And out O1 which we have calculated is 0.75136,507, and the out O2 which we have already calculated is 0.772928,465. So we have already calculated in our step 1 the predicted value of y, that is based on the random weight we have initialized for our network. The network says for my input 0.5 I1 and for my second input I2 which is 0.1, the predicted values of y are O1 is equal to this one and the predicted value for my output node O2 is this one, right? But we know the actual value of y. So my actual value of O1 and actual value of O2. So we know from the graph, from our network, that the actual value of O1 according to my labeled data set is 0.01, and for O2 it is 0.99. So this is 0.01 and this is 0.99, right? So the next step, which is the step 2 of my forward propagation, is to calculate the total error using what we call as our loss function. We also call this as a cost function or sometimes as an error function. And we will use a simple cost function, which is the square errored function, that is E total is nothing but summation of half into the actual value of my output minus the predicted value according to my network, the whole square. So let us do that for first find the error for E of 0, 1, then find the error of the output node E2, and then calculate E total, which will be E of 0, 1 plus E of O2, right? So let us first find E of O2, which is equal to half into the actual value of my output node O2 is 0, 1. So 0.01 minus the predicted value for O2 according to our network was this, that is 0.75136507, the whole square. And when you calculate this value, we get this EO1 to be 0.27481183. And similarly, we do it for the E2, the error in the node output node EO2, which is half into the actual value of output for O2 is 0.99 minus, we have already calculated the predicted value for O2, which is nothing but this particular value, which is minus 0.77292845, the whole square, which when we compute is equal to 0.0235660026. And once we have got that, we now compute the total error of my network for the input 0.05 and 0.10 for I1 and I2 respectively is equal to, we add EO1 plus EO2 and we get E total is equal to 0.2983711009. So this is what my total error for my network is. So we have completed forward propagation. The next thing that happens during the training of a neural network is to do the backward propagation. And in backward propagation, what we will do is we will try to adjust these weight. So we have already calculated the weights or we have already initialized these weights for my network, right? And this was a random initialization of the weights, and based on this weight, this is what my error is for my network. So what backpropagation does is the backpropagation will change these weights or try to adjust these weights so that my total error becomes minimum. So that is what a backpropagation does. And let's see how a backpropagation works with this same example.